All right. One of the things we did, which was we saw that the most important parameter in a feedback system is the asymptotic transfer function, or asymptotic gain, or more generally asymptotic transfer function, which is basically what the feedback loop looks like when you have a lot of feedback. When the amount of gain that you have in the feedback system is basically approaching infinity. And the way we achieved that was basically taking a source and setting its value, a dependent source, and adding a value k to its, multiplying by value k, and taking that k to infinity. And that gave us what we call the H infinity, right? H subscript infinity. It has nothing to do with H infinity control or anything like that. So it's the asymptotic transfer gain. Now, that is an approximation, right? For infinite k, for infinite gain. The question is that what happens in a real circuit? So what we will do now, we will define an important parameter, namely return ratio. And using that parameter, we will come up with an equation, with a formula, which is called asymptotic transfer function, or sometimes people generally call it asymptotic gain formula, but would like to call it asymptotic transfer function formula, which is a more general statement. That would be exact and gives you two correction factors that you can use that relate to two different things in any feedback loop that exactly tell you what the transfer function looks like in terms of H infinity and how H infinity gets modified. Right? So we can use that for design again, because what it does is say, well, okay, I want to get a transfer function of 10. I define an H infinity. If I define an H infinity of 10, I have this correction factor, so I have to make my H infinity 11 or modify these other parameters of the circuit to get it to what I want it to be. So, okay, so let's talk about what we mean. The parameter that's very important here is the so-called return ratio. This is a parameter that was defined by Bode, of the Bode plot initially. And he defined it in a slightly different way from the way we define it. He defined it in terms of determinant and all those things, and we'll talk about that briefly later on, what that definition really is and how that general definition applies. But we are trying to kind of find something that's more visualizable, so we can actually visualize. So imagine that in the circuits, right? So you have a circuit, you have some network, and inside that network somewhere, there's a dependent source. Right? In general, this dependent source could be a current source or a voltage source. Now, let's say and this is a dependent source. Let's say it's a current source, for example, that depends on some other parameter, some UA. So there's a UI, the input, and UO, the output. Now, why do we show them as UI and UO? Because they could be current or voltages. So in general, if we know what they are, we should show it as VI and VO, or II and VO. Or they can be different parameters, different voltages current. So there's some sort of a dependent source somewhere in your circuit, right? With some sort of a gain. So it's GUA. Now, what the return ratio, the calculation means. So here's the thing, just listen to this carefully because it's important, and then we'll see how we do it. It means that if you want to find what the return ratio is, it says, take this dependent source, replace it with an independent source, exactly where it was. So this is a new circuit. And make this independent source, let's call it whatever. In this case, this was a current source. Or let's call it, just keep it in general. So this independent source, let's call it UX. Okay? Apply an independent source UX and see what the dependent source would have gotten if it was sitting here. So this is that dependent source that we had, GUA. And take that quantity to be called UY. In other words, replace your dependent source with an independent source. Say, if I drive where this dependent source is with an independent source, UX, right? What would come back to this source? What would this source now, if it were a dependent source, would produce? Okay, so it's a little bit of a, but once we see it, and then define that ratio as the ratio of what comes back, UY to UX, as the return ratio. So what do we mean by this? Again, let me just repeat. So let's do a more specific example. Let's say this is a current source. Let's say this was a current. Well, let's just put it this way. This is a current source. It says, take this current source out, replace it with an independent current source of value Ix, and let the circuit do its thing. And it basically, by the way, null the independent source. So Ui is 0, and the input is 0. The independent sources are 0. And see what the circuit would, what fraction of this thing comes back to produce an Iy if this was that dependent current source was sitting here. I'll put it this way. Okay? It sounds like a kind of a complex thing to do, right? It isn't when you actually do it. Now, there's actually a better way. Yes? No. Iy, it's basically just saying that what would come out of Iy. You can imagine even Iy being not here. You can imagine Iy being sitting. So let's say I make a dependent current source here that produces the Iy, which is going to be GUA. The only reason you really need to have this step is that if there's some gain associated with this, like this G associated with your current source, you could say simply Iy is GUA and not draw this. But you want it to be of the same quantity. For example, let's say if this is a transconductance, right? This UA could be a voltage. This is a current, right? To produce another current, you need to multiply it by that transconductance, for example, right? To get these things to be of the same units. So your return ratio is unitless. Your return ratio is always unitless, right? So this looks kind of messy and ugly, right? So what we actually do is something that, again, initially make it even more confusing, but it shouldn't. So what we do is the following. We say, let's say this was a current source. If this were a current source, let me clean it up a little bit. So this was our dependent current source sitting here, GUA, right? What we would do is say, we introduce this current source exactly in parallel with it and call it IZ. So we know, and then let's look at this. This we call Ix, and this current we call Iy. We know clearly that Iy plus Iz is Ix, right, from KCL at this node. And I'll tell you why we did do this in a second, but let's then tell you what the procedure is, and then we'll say what we do. What you do, you generate an Ix here, and you measure this Iy. And the ratio of this Iy to Ix is your loop gain. I'm sorry, not loop gain, your return ratio. Okay? Now, why did we do this Iz thing? This Iz is just to add an extra degree of freedom so you can control Ix and Iy independently, right? It creates some independence between Ix and Iy, so they're not dependent on each other. And in these calculations, Iz should never enter your calculations. It's a way for the circuit to look meaningful, not open current sources and all those things. So all you care about is Ix and Iy. So essentially, this is equivalent to what we did here. But it's a cleaner way, so you don't have to take these sources outside the circuit and all those things. Once we do examples, it becomes very clear what I mean by that. So this is the definition. And now, what if my source was a dependent voltage source? So what if we had a dependent voltage source? So let's say, again, Ui, Uo, and Ua, that's the parameter that's used for the control voltage. How would we do that? How would we deal with that now, if I wanted to create a Vx and Vy? We introduce, again, a voltage source in series. Let's call it Vz. And this is going to be Vx, and this is going to be Vy. Again, it's clear that Vx is Vy plus Vz. And again, Vz should not enter the equations, your calculations at all. In other words, what you say is that I have a Vx here. It goes through the network. It comes back. It produces a Vy here. I want to see what that is. Or I have an Ix here. It goes through the feedback inside the circuit, and it produces an IY. And the negative of that ratio is going to be the return ratio. So the return ratio here would be negative IY over IX, and here it would be negative VY over VX. In general, negative UY over UX. So this is a definition thing, really. And we'll see how it comes to be useful. And before we do that, we also have to do a derivation to see the full usage of this thing, of that formula. So I'm going to tell you what we are going to be deriving first. Okay? I'm going to tell you the answer, and then we'll do the derivation. So in case you don't want to kind of like, you want to tune out for the derivation for 5 minutes or something like that, when we do the derivation, you can tune out. But the key result is the following. The key result is that the transfer function of the circuit, in general, defined as UO over UI, is exactly H infinity, the asymptotic transfer function, times T over 1 plus T, where T is the return ratio, plus H0, 1 over 1 plus T. Now, H infinity, we know what it is, right? H infinity is that you take a source, you put a K in front of it, and you take that K to infinity, right? So that's the transfer function when that K is infinity. T is the return ratio with respect to that exact source. H0 is the only thing that's not undefined right now, right? H0 is called the direct forward transfer, which is basically the transfer function when that K that we set to infinity, you set it to 0. Meaning you kill that source. And see if there's any other path for the signal to make it to the output. And we'll talk about how this happens and where it happens in a few minutes, just like in terms of what the implications are. But this is the end result, and an important result. This is the asymptotic transfer function formula. Also known as asymptotic gain formula. That's a more common name for it. And it's exact. So these are the correction factors to this. And we'll talk about these. We'll see examples of this in a few minutes. But that's what it is. But let me first do the derivation. Let me do the derivation of this thing. How do you determine this asymptotic transfer function formula? Where do you get it? So the derivation is like this. So let's say you have a box with a UI and UO. And then there is a UA inside. And then there is a source that is GUA. Right? This could be a current source. This could be a voltage source, etc., etc. Now, and then you're inducing a UX. So this is GUA. And you're introducing so this is another source. What I'm showing right now implies that's the current source. So if it were a voltage source, you would put it in series. So, but I'm just going to show it as UX and UY. Okay? So you have a source of an independent source that produces some sort of UX to the circuit. Now, there are really two things that we want to know, right? There's a UO and then there's a UA, this voltage. That are the parameters that we want to find out. And there are things that we actually induce ourselves, which are basically the UI, the input, and UX. Right? This is UZ, if you will. So I can write this, if it's a linear circuit, I can write it as a linear combination of these four. So I can write it as A times this, B times that, C times this, plus D times that. So in the general case, this is the relationship that you have. All right. Now, imagine that actually there is no test source. So the original system, when you don't have this test source UZ, so basically we are saying UZ equals 0. So this is the system in its normal behavior condition, is what do we get? Well, this obviously, in that case, we know that uy is going to be ux. Uy is equal to ux, right? Because the uz was the difference between them. Now, therefore, this equation becomes u naught, u0, u out, a ui plus b uy, and then this becomes ua equals cui plus d uy. Right? Now, also assume, so now we want to find out what is the transfer function in this case. Now, let's do it a little bit more general. Let's assume that this is also scaled by a factor of k. Because then we can set k to different values, and if we set to k to equal 1, k being 1 is the normal transfer function. And then we also can express it in terms of asymptotic transfer function when k goes to infinity and all those things. So we can get one equation that captures more of these things. So what is that transfer function? Right? So let's find out. We are trying to find out what this is. Now, in this case, uy is simply kgua, right? So I can replace that with this. So I can say A is u plus kgb ua, kgb shows up here, and then c ui plus d, or kgd ua. Okay. So now you can see you can solve for uo in terms of ui. Right? Because you can eliminate UA. I have two equations, two unknowns. I mean, right? What we are interested in is the transfer function, right? We are interested in the transfer function h, which is defined as UO over UA. UO over UI. So this is what we are trying to determine. This is what we are trying to evaluate. When UZ, so this is the transfer function for that when UZ is 0. Basically, we don't have that extra funny source. Okay, so we need to solve for UA from this one and plug it into that guy, right? So if I solve for UA from one of them, I get, what do we get? You get, you move this one to the other side. So UA is C divided by 1 minus KGD KGD times UI. From this one. UA is C over 1 minus KGD UI. And I plug this into this guy, this UI, so I will get what I get, right? We'll get UA is A, or maybe write it better. UO over UI is going to be A plus KGBC divided by 1 minus KGD. Okay, so that's what it would be. So I can write it here in this form. So I can take this and say this is equal to that. That's the transfer function. But we'll do something else to make it a little bit more meaningful. So now that we have this transfer function, let's actually do that. Let me just write it exactly in those terms. 1 minus KGD. Okay, but we are interested in two things. There are two special cases of the transfer function we are interested in. The H infinity and H0. What is H infinity? So H infinity, right? So we can write this here. H infinity is H when K goes to infinity, right? So when K goes to infinity, what is this value of H for K being infinity? What do we get? A minus, right? You have the A remains, right? A minus BC over D. Because this term becomes insignificant, you get A minus BC over D, right? Oops, not here. Sorry. Here. A minus BC over D. And when K is 0, what do we get? Obviously, this disappears, you just get A. So what we'll try to do is try to see if we can reorder these terms in such a way that these two terms show up. And if you do that, it's pretty straightforward basic algebra. What you will get is this. You get A minus BC over D times negative KGD over 1 minus KGD. It's just basic algebra with this. Plus A times 1 minus KGD. 1 over 1 minus KGD. Right? It's a very basic step. Now, okay, now what? Well, we know this is H infinity. And this is H0. So if we find out what KG, negative KGD is, then we are done. So what is negative KGD? Well, now you can actually apply this UZ, right? So now imagine that UI, because when you're trying to how do you determine return ratio? You set the independent sources to 0, which basically means that UI is 0. So now we are doing the calculation of return ratio. So we say return ratio. How do you calculate it? You set UI to 0. And if you set UI to 0, what do you get here? UA is going to be DUX, right? So UA becomes DUX. But then, what is UY? If UA is DUX, UY is just KG times that, right? We know that UY is K times G, that's what we have, times UA, which basically becomes KGDUX. Therefore, the return ratio, which is negative of UY over UX, it's defined as that, is going to be negative KGD. Therefore, this equation simply produces H infinity T over 1 over T plus H0 1 over 1 plus T, which is the result that we claim. So this is what we have, which is the result that we claim we were trying to obtain. This is the asymptotic transfer function formula. So that proves it. That's the derivation. Okay, so now that we derived it, we know it's true. Let's see what it means and how we use it. So this is one way to write it. There's another way to write this, which is in a multiplicative correction term. So basically you can write it as H infinity d sub t d sub 0. So it means that your transfer function is just H infinity that we calculated before times two correction factors. Now dt is t over 1 plus t, right? So which basically, if you look at it, you see it's less than 1. And when t becomes large, when your return ratio becomes large, which basically means that you have a lot of feedback, it approaches 1. So it shows that if you want this correction factor not to be large, one of the ways is basically by making the feedback very large, having a lot of feedback. How about d0? d0 is 1 plus h0 over h infinity times t, which again can be made close to 1, can approach 1 if t becomes very large, right? Or your h0 becomes very small. Now, what is this term? So we know this what this is. This is really h infinity is what the loop does with maximum feedback, with a lot of feedback. The return ratio, we know it's a measure of how much of the signal that this dependent source generates comes back to itself, right? It's a measure of the feedback. What is this a measure of, this h0? It's called direct transfer function, direct transfer. Direct forward transfer, actually. Forward transfer. Well, in a feedback loop, for example, if you have something that looks like this, ui plus, ui minus, a, and f, this can be a measure of how much of the signal actually travels through your feedback path itself, backwards. Because, for example, it can be a resistive network, right? So some signal can just go through that, or some other path, some parasitic paths. Doesn't even have to be the feedback path. It's a measure of how much of the signal actually goes forward just because of this network being there. And these networks are not necessarily unilateral, meaning that they transfer signal from this direction, from right to left, but they can also transfer signal from left to right. So all of that is taken into account. Now, there's one key thing to be noted, which is that if you are using this, the return ratio needs to be calculated with respect to the same source, or for the same source that you use to calculate your H infinity and H zero. You can't calculate your H infinity for a different source and come back and use a return ratio from a different source. You can, you get the wrong result. You shouldn't. Okay? So this holds as long as all three of them are calculated with respect to the same source. So much for that derivation. And let's do examples, because I think then we will see how this works a lot better. So we are going to do a few examples of these. Let me see. Yeah, let's go here. And our first example is what we call the shunt series feedback, one of the shunt series feedback stages that we had before. So it looks like this. So you have a input stage. There's a resistor R1. There's a resistor R2. The resistor R3. You go to a second common source. Oh, no, this is not actually a common source. Never. This is actually resistor R4. And then coming down here, we were taking our output from here, V out. Our input was a current source, I in. So this is a circuit we looked at before from an asymptotic transfer function, H infinity perspective, but we are going to do the full analysis for it now and see how things change. So what do we have here? First of all, you have to check the sign of the feedback. So let's see. If this node goes up, what happens to this node? This is an inverting state from here to there, right? It's a common emitter or common source. So this goes down, which basically means that this node goes down. Now from here to there, you have a follower. So this will also follow, which will basically mean that this comes back down. So the feedback is negative in this arrangement at low frequencies, essentially. And now that we know that the feedback is negative, we can apply the asymptotic transfer function formula. To do that, let's calculate several different parameters. So first, we did this before, but we will do it quickly. So let's say this is the source of interest. So we are thinking about this as really a pi model. So this is a GMV pi here, right? So we have a GMV pi, and we want to calculate k GMV pi. So if we make that k infinity, so k going to infinity here, what do we get? It means that the input, the VGS or V pi of this thing should be 0, right, to get a finite output. So if this voltage is 0, so this voltage from small signal perspective is 0, obviously this current will be 0 too. Has to be, right? Because the voltage is 0. Now, therefore, that means that this current I in is going through here, which means that this voltage, V in, is going to be negative, and the voltage here is 0, so it's going to be negative of R1 I in. Therefore, this current is going to be this voltage divided by R2, which is going to be negative R1, negative R1 over R2 times I in, right? So this total current is the sum of this current and that current, so which is basically negative I in plus this, which is negative I in times R1 over R2 It's negative I in times 1 plus R1 over R2, which is the same current that's pulled out of here, which would be multiplied by negative R2 to generate the output, right? So if you multiply that by negative R2, then V out is going to be essentially, or R4, sorry, would be I in times R4 times 1 plus R1 over R2. Therefore, your H infinity, which is H when K goes to infinity, is R4, or defined also as the ratio of, so let me define it this way, V out over I in when K goes to infinity is going to be R4 times 1 plus R1 over R2. So this is what we calculated last time, right? We know this when we were talking about this. We did calculate this. I'm just redoing it quickly. This is the asymptotic transfer function. This is what the ideal feedback system would do. So if you need a transconductance of 5 kilo ohm, you can make this, for example, R1 1 kilo ohm, and make this ratio of R1 to R2 4 kilo ohm and 1 kilo ohm, if you're designing very quickly, the 5-second design exercise, right? So now we want to see how close or how far it is from the actual answer, the correct exact transfer function. Okay, so to do that, we need to calculate the return ratio. The second thing you calculate is the return ratio, really. For return ratio, this is what we do. So because that's where our current source is, that our dependent current source is, I put a current source IZ here, which should never enter any equation. What it does, it produces an IX here and an IY there. The role of IZ is just to make sure, be able to generate a situation where IX and IY can be different. It just supplies the difference between those. That's all it does. So we have an IX here, so let's calculate the return ratio. How do we go about that? If this is IX, what is this voltage? Negative IX R3, right? So this is going to be negative IX R3. So if that's negative IX R3, then what do we get here?
Negative IX R3 minus VT.
Well, you're thinking large signal, right? You say VT. We are doing a small signal analysis, right? So it's, what do we have? We have a follower, right? What do we have in this model? The easiest way to think about this is the T model, right? You have an RM and R2. There's no current flowing in this direction. So by the way, when we are doing the return ratio, this is gone. So this is gone for return ratio. Okay? So there's no current flowing in this direction, right? So it would be a resistive divider between R2 and RM. It's a source follower. So it would be R2. So this voltage would be IX R3 times R2 over RM plus RM, whatever, 2 plus R2. That's this voltage, which is going to be the same as this voltage because there's no current flowing here in this case. So if this voltage is that, then what is this IX? Or IY, I'm sorry, what is the IY? Now the IY is going to be that times GM1, correct? That's the VGS of this thing. This voltage produces a current here, a voltage here, which is the same voltage, and then it produces this current through a GM1. So IY is going to be GM1 times that thing, which doesn't fit here. So let's write it here. So we can say IY is going to be GM1 times this, which you can write as negative GM1 R3 R2 over RM plus R2 IX. So if we ask what is the return ratio, which is defined as negative IY over IX, is going to be GM1 R3 R2 over R2 plus RM2. So that's the return ratio. Do you see how it's calculated? So now, is this return ratio large or small? So what is our correction factor? T over T plus 1, right? We can actually calculate it, right? If you want to calculate that, dt t, which is t over t plus 1, is this times itself, this divided by 1 plus that. So you can actually write it as GM. You can also, if you want to, I prefer it this way, but if you want to write it as all GMs, you can write it as GM1 R3, GM2 R2 times, or the whole thing divided by, actually. So it's GM1, GM2, R2, R3 divided by 1 plus GM2, R2. I multiplied the numerator and denominator of this thing by GM2. That's all I've done. Okay? So that's one quantity, another way to write it. And then if you take this and plug it into that equation here, you will get GM1, GM2, R2, R3 divided by 1 plus this times that, right? You get 1 plus GM plus GM1, GM2, R2, R3. So you get something like that. Now, what do you want it to be for the feedback to operate close to ideal? You want this t to be as large as possible, or dt to be as close to 1 as possible, right? So how can you make t as large as possible? Well, this is a ratio less than 1. If you choose R2 not too small, you can make this to be close to 1, so it doesn't introduce a significant attenuation. Let's say your RM is, I don't know, it's like 100 ohms. You make this a kilo ohm, and then you get a factor of 0.9, roughly, right? Or close to 0.9. And then you have the GM1R3, which is the gain of this stage, right? So you want the gain of this stage, GM1R3, to be relatively large. So if you make that, let's say, 50, then this is going to be 50 over 50 plus 1, roughly, right? On the order of 50. So it's going to be 0.98. It's going to be 2% off, roughly. Is it a big thing? Usually not. You can make an adjustment, correction. So this is the correction. This is one of the correction factors. Now, we've done 2 out of 3 things. There's something else we need to calculate. All right. We need to also calculate H0. How do we calculate H0? H0, we just basically kill this dependent source. So this independent source is gone for other calculations. So this is not there. There's a dependent source in here. That's dependent source of the hybrid pi model, right? The pi model. So when k is 0, k equals 0, that source is gone. So there's no signal generated here. There's nothing going here, right? So would there be any signal at the output? Is there another path for an input signal? Now for this, the IN is there. Is there a path for this IN to make some output signal? If this is not doing it, it's as if this doesn't exist. You can think about this doesn't exist. Is there a path for the signal to get to the output? Do you see a path? How about through here? Through the feedback network. What is it? Well, if this doesn't exist, this is IN. This current is 0 anyway because it's the base of the gate of a common of a MOSFET. So this is going to be IN, right? So you are injecting IN into this branch. How much of this IN would go this way? What fraction of IN will go? So it gets divided, right? It's a current divider between what and what? R2 and RM2, right? So what fraction goes there? R2 divided by R2 plus RM2 will go there. And that would show up exactly here, right? The same current, because that gain is 1. So now, from that perspective, this is a common gate. Right? So it goes through, and it goes through what? Then it goes through R4. Right? It gets dumped into R4, so it produces a voltage. So H0, which is defined as V out over IN when K is 0, is going to be this voltage, which is basically R4, times R2 divided by R2 plus RM2, which if you really insist, you can write as GM2R2 divided by 1 plus GM2R2 R4. So that's H0. Right? Now, is H0 small or large? Let's look at this. H0 is R4 times something less than 1. So there's some fraction of it. There's some element of that. Now, how large it is, you can calculate it for the parameters of the circuit. But now, if you take these three, you can write this overall transfer function in the following form. So I'm going to just aggregate all of these things into one expression. So you can write H equals H infinity dt d0, which you can write as R4 1 plus R1 over R2, which is this part, the H infinity part down here, times this dt, which is GM1, GM2, R2, R3 divided by 1 plus GM2, R2, 1 plus GM1, R3. And I am doing this for reason. 1 plus, and then you get that third correction factor, R2 over R1 plus R2, GM1, R3. Which you can also write, now, if you aggregate everything, you get something like this. It's in there, it's in the handouts. I'm trying to make a point, actually, by writing these this way. GM1 R3. Okay, I think I'm done. Oh, okay. With that, so my question to you is that which one of these two forms, this form or this form, is preferable? The one on the top or the first one or the second one? The first one seems longer, right? Looks like a longer, more thick. And we say this is a more compact result. Yes, it's a more compact result. This is what you get if you write K-scale and KVL. That second part, second form. But it's useless, or less useful at least, right? Because it's hard to tell what affects what. If I'm designing, that's useless. And if I'm analyzing, okay, fine, but then a computer can do a better job at that. So what are we doing, really? The first form, even better than the first form, is basically looking at these three quantities. Looking at this, and looking at this. Standard. You remember when we were doing time constants, you said you could just aggregate them, right? Just one giant transfer function. But it's the use more, you're removing information. You're not adding information by doing that. When we go from this to this, you're removing information. Because you're mixing, blending everything together. What this tells you is that, look, 5 second design, this is your path. And it says, how close are you going to be? Make sure that this ratio, or even better, if you look at it this way, you make sure this is large. Make this large so that this doesn't deviate too much from that. This has to be large. Make it large. Large enough. And that gives you a sense of how far off you are. If you make this whole parameter 100, then you are going to be 1 by 1% because of this correction factor. And you don't exactly care beyond a certain point. You want to be close enough, right? And then this says, okay, this is how much signal gets through the feedback network itself. How much is basically leaking through this feedback network. Even if the circuit didn't exist, the active part of the feedback part of the network, the forward path of the system didn't exist, this is how much it goes through these other paths. And in fact, this is funny, because this is interesting, because sometimes this feed forward through this direct forward transfer can produce an overshoot in your response. if you have capacitors and all those things, you can be in a situation that you will see an overshoot and say, oh, my circuit is underdamped, something like that. It may have nothing to do with that. It's just this path being a high-pass path, just providing, if you make that there's a high-pass component to that, some signal can pass through that and just produce a little bit of a local overshoot. Essentially, it's producing a zero in the transfer function. So that's another example. One example, at least, per se. OK, let's do another example. Any questions on this example? All right. So let's do another example. And this is, again, another one of our examples that we've looked at before from an asymptotic transfer function perspective, but we'll do the full analysis for this to see how it behaves. So this is the circuit we looked at last time. So we had this stage, and we had a resistive divider here that fed this guy. This was R3, I believe. This was a cascode, so there was a V bias. I think this was R2 and R1, but I will double check to make sure it's not the other way around. This was an M1. There is an input current source, I in, and output voltage source, V out. Right? So we are looking at it from a small signal perspective. Is it R2 and R1? Yeah. OK. So this is a circuit. Again, it's a transimpedance amplifier, if you will. There's an output to input ratio that's determined by this. So now we did the asymptotic transfer function before, but let's do it quickly again. For doing that, and I will draw the small signal model next to it just for you to see how it looks like. So this is going, basically, this is your so you have a GM1 V1, let's call this V1, and then you have a, here we use the T model. So let's call this IS2, and this is IS2, and this is R3 to ground, and this is V out. And now this is our I in. So again, three parameters, H infinity, T, and H0, in that order. I think they're important in that order usually. H infinity is the most important parameter, then it's the T, the return ratio, then it's H0. If you're short of time, this is the order we calculate these things. Okay, so we used, I had used blue there for H infinity. So H infinity calculations. Let's do H infinity calculations. So what do? What source do we pick? Well, we can either pick any of these sources. Let's pick this one. Okay, so we make this K IS2. And we will, for H infinity, we set K to go to infinity. We let K go to infinity. When K goes to infinity, and we have checked the sign of this feedback, we know it's negative feedback from before. You can double check it. So we know that we are trying to produce a finite output with an infinite dependent current source with a gain of infinity, which basically means that the only way this is going to work is that this is going to be 0. If that current is 0, this voltage is also 0. Right? Which basically means that all of this current, the feedback loop must operate in such a way that this current becomes exactly I in for this to work. Otherwise, there's no other way. So if this is I in, so we know GM1 V1 is I in. But we know what V1 is in terms of V out. It's a resistive divider, right? So V1 itself is V out times R1 over R1 plus R2. We did this before, so I'm going to do it very quickly. So, and then we plug this into here, you get GM1 R1 divided by R1 plus R2 is going to be equal to times VO is I in. Therefore, H infinity, which is VO over I in, when K is infinity, is going to be just this. It's going to be GM1 R1 over R1 plus R2. Okay? No, sorry, the other way around. It's V over IN, so it basically becomes 1 over GM1 times 1 plus R2 over R1. That makes more sense. So it's the GM of this transistor, 1 over GM of the RM of this transistor, and scaled by 1 plus R2 over R1, which is basically the ratio that you see in the resistive divider. We've seen this before. This is H infinity. So now let's calculate the, so now what we need, the next thing is the return ratio, right? How do we calculate the return ratio? The way we calculate the return ratio is that we introduce this now IZ here. So this is IX and this is IY. Sorry, they're very close to each other right now. And IZ, again, never enters the calculations. Never. Or VZ. Never. It never enters. So if you had a VZ or IZ in there, you're doing something wrong. It's just a way of showing it without changing the drawing funny-looking schematics. OK, so if this is IX, right, what are we trying to calculate? We need to calculate V1, and from that, so, and for this calculation, of course, IN is not there, right? Because it's just basically null the independent source, null the input. So what is IY in terms of IX? So if this is IX, what is the current doing in between these two? So it's going to be current divided between these two, right? So this current is going to be IX times the division ratio between these two branches. What is the division ratio between those two branches? It's going to be R3 divided by R1 plus R2, which is the resistance here, plus R3. Right? It's the division ratio between this resistor and that resistor. The current divider between those. So that's the current that gets pulled out of this guy. So V1 is going to be this times R1 with a minus sign. Right? So V1 is going to be IX, or negative IX, R1, R3 over R1 plus R2 plus R3. And then from that, you know what this current is, which is the same as this current, which is the same as that IY. So from that, you know IY is going to be GM times that, GM1 times that. Negative IX, GM1, R3, R1 over R1 plus R2 plus R3. Therefore, your return ratio, which is defined as IY over IX with a minus sign, negative of that, is going to be GM1 R3, R1 over R1 plus R2 plus R3. Now, if you want this to be large, what do? Bless you. You see, you have this quantity is less than 1, right? That's an attenuation between R1, R2, and R3. So it means that make sure that your R2 plus R3 is not significantly larger than R1 when you're designing, right? Because you don't, unless you want it to make, otherwise you will have to make up for it with this guy. So let's say whatever, you've picked this to be 0.8. This ratio. You can pick some values, right? You've picked your R3 to be 5 kilo ohm, and then you make this, like, for example, be whatever you want it to be. Like, let's say 4 kilo ohm and 1 kilo ohm. So this becomes 5 kilo ohm, and that's 5 kilo ohm. So then you basically have 1/10 in that case. So that would be not very good. If you make this, for example, 50 kilo ohm and 10 kilo ohms, then you have a situation where you have a reasonably better chance, but still this ratio is there. So you may be better off having this ratio being, let's say, for example, 1, so that this reduction is not too large. But regardless, what it means is that you need primarily, you need the GM of this transistor times this resistor. That's what determines what your gain is, the overall gain of the system is. And hence the return ratio of the system, which you want it to be large. So that's the return ratio. Now, how about the direct forward transfer in this case? What is a direct forward transfer? So for direct forward transfer, this is back in, right? So you have an IN. But now you're setting K to 0. So now K goes to 0. So in this circuit diagram, the way we've drawn it, do you see any pathway for signal to get from the input to the output if that k is 0, if that current source disappears, if this dependent current source is not there? Because that's what k equals 0 means, right? Becomes open loop, open circuit. Is there a pathway? Do you see a path for the signal to get from the input to? No, there isn't. So in this case, H0 is very simple. H0 is 0. So it's even simpler. So your gain, your transfer function, an exact transfer function is H is your H infinity times T over 1 plus T. Exactly. This is the correction factor for it. Now, one of the things to be mindful of in these examples is that these different stages can be in different configurations for different calculations, right? For example, in the previous example, just let's go back to that for a second. This is something I meant to say then, and I forgot. If you think about this, this transistor is an interesting one, because for the forward calculations, for the gain calculation, for the asymptotic transfer function calculation, right, from here to there, this stage is in what configuration? So from this path, the signal gets from here to there, and then from here to there. It is it's a common emitter, right? Or common source. Actually, a common source with source degeneration, right? So for this calculation, or for the as far as forward path is concerned, this is a common source. Now, for the return ratio calculation, what's happening in the feedback loop, when we went from here to there, that was a source follower or common drain, right? And interestingly, for the direct forward transfer calculation, when we went from here to there, it was actually in common gate. So the same transistor is viewed in three different configurations for these three different calculations. An interesting side note. The point is that the same transistor, it's meaningless to say this transistor in general is in a common source or common drain or common gate. You have to say for which input and which output, for which signal, for which calculation. I mean, and it sounds trivial, but something that sometimes throw people off, can throw you off. Okay, so that was another example. Let's do one more. Okay, so let's take this example that we had and then make it a little bit frequency dependent to see what happens when you have frequency dependence in these things. So now we'll take the same circuit, but now introduce two capacitors. Let's call this C1 and C2. So we are introducing two capacitors in this circuit. We want to see how these things work, because these things actually should work as a function of frequency too. And generally, they are all functions of frequencies. So we'll see how that works. So let's see how our calculations change if we do this. Let's go starting with the most important calculations, which is H infinity. So let's look at that. So basically, now we have a capacitor here, C2, and then we have a capacitor here, C1. So what happens for when k goes to infinity here, right, means that this voltage and this current are still forced to be 0, both the current and the voltage. Now, the voltage across this capacitor is 0. So it draws no current. So it has no role in this calculation. It doesn't mean that it has no role at all. It means that for H infinity, it has no role. So in H infinity calculations, this capacitor plays no role. So what is the thing that does play a role? Is this guy, because now we saw before that this does play a role. Because now your transfer function has this when you go around, this does have you have a low pass response in your feedback network. And you remember what it did to the transfer function, right? We did this calculation before. It modified it by a 0. So there was a tau z, it produced a 0 s in this transfer function, if you remember from our previous example. So essentially, this H infinity of s, that's another way of saying this, is that H infinity of s was h infinity of 0, which we calculated before. So let me just remove this. And let's call this h infinity of 0 times 1 plus tau zs. And tau z here was, if I'm not mistaken, it was R1 parallel R2 C1. Yes. No, actually it's R1 C1. No, it's correct. R1 parallel R2 C1. This was correct, what I said. It's correct. Okay. So that's what, this is the way the h infinity changes. So you can see that if your feedback network was perfect, if you had the transfer function, the return ratio was infinity, then you actually get a 0. You actually get a transfer constant, the asymptotic gain that will go up with frequency. Of course, this can't be true forever, right? Because then your t starts dropping, and at some point the t dropping will produce some drop in the overall response, because this will start mattering. Okay, so let's calculate the other parameters for this. Let's see what the other parameters are. So, for example, now let's go and look at the return ratio. See how the return ratio changes. How would the return ratio change? Well, how did we calculate the return ratio? We said this is Ix. We saw what comes out. So now you have a resistive divider here in this path. Now, one thing that we can pay attention to when we are calculating the return ratio is that now, how many poles and how many zeros from a return ratio calculation perspective we have? Meaning the transfer function from this Ix to this Iy. That's the return ratio, right? We have developed all these tools and techniques for calculating and determining this. What is it? How many poles do we have for that transfer function, and how many zeros? How many poles? Remember, for that calculation, this is not here. And k is 1 for that calculation. So there are 3 calculations really, with the k0, k1, and k infinity. So k is 1, and you have an Ix and an Iy. How many zeros and how many poles? How many degrees of freedom do we have? We have 2 capacitors, right? And we are not going to k infinity, so this voltage is not necessarily 0. So this capacitor is there. And this capacitor is there, so these two are not forming a capacitive loop. So you have 2 poles, exactly. And how many zeros? Is there a combination? What is the largest number of elements that we can simultaneously infinite value that would produce a non-zero transfer function? If you infinite value this guy, you get nothing at the output, right? Nothing will come back. If you infinite value this one, nothing will come back. So there are no zeros in the return ratio. So this is a different quantity you're calculating. The return ratio, T, doesn't have any zeros. It has 2 poles. Now, there's one more thing actually you can tell that makes our lives a lot easier too. These 2 poles, are they coupled, or these 2 time constants more accurately, are they coupled or uncoupled? How do we check? Does the time constant for one changes if we short circuit or open circuit the other one? No. If I short circuit or open circuit this guy, it wouldn't change the resistance seen by this guy, right? And since there are only 2, it has to be reflective, right? So it means that the other one cannot see it either. So these are 2 uncoupled poles, 2 time constants corresponding to 2 real poles. What are those time constants? There's a tau 1 and tau 2. So there's a tau 1 0 really, which is tau. So I call it tau 1 because it's equal to tau 1 0. What is tau 1 associated with this capacitor? It's C1 times what resistor? What is the resistance C? Yeah, because if you null the independent source, we set Ix to 0, it becomes open circuit, right? Here. Now, you said R1 parallel R2 plus R3. So it's C1 times R1 parallel R2 plus R3. So that's one time constant associated with this guy. And tau 2 is what? What is the resistance seen by this guy? It's very simple. Just the RM2, right? This guy. Rm2. So it's going to be C2 Rm2. So those are the two time constants. So what is my, I know what my low frequency loop, the return ratio is, right? And therefore, the high frequency return ratio, T of S, is going to be T0, which is that quantity. Let's call this T of 0. T of 0 divided by 1 plus tau 1s times 1 plus tau 2s. So this is the way it becomes a function of frequency, and this is the way this guy becomes. How about H0? Would H0 change from 0 as for these capacitors that we've introduced? No, because still, if this is gone, nothing will make it to the output. There's no pathway for it to make it to the output. So H0 is still 0. So H0 of S is also 0. You can write it as H0 of S. So our general new transfer function, the overall transfer function, H of S is H infinity of S times T of S over 1 plus T of S. So this, we know what it is. It's just a 0, right? Introduced in the loop. Let's look at this quantity, see what happens here. So if I get T of S and plug it into this thing, so the question is, what is T of S over 1 plus T of S? So look at this. We plug these in. You get T of 0 over 1 plus tau 1s, 1 plus tau 2s, divided by 1 plus that. So if I do the 1 plus right here, you get 1 plus tau 1s times 1 plus tau 2s plus T of 0 divided by those two. So these guys cancel these guys. Okay? So what you're left with is T of 0 divided by 1 plus T of 0 plus tau 1 plus tau 2s plus tau 1 tau 2s squared. Now, if you factor the DC part of this thing, which is T of 0 over 1 plus T of 0, what you end up with is this. You end up with 1 plus B1s plus some B2s squared, and B1 would be tau 1 plus tau 2 over 1 plus T of 0, and B2 would be tau 1 tau 2 over 1 plus T of 0. So what's happening as you see is that T of 0, as your low frequency return ratio increases, what's happening to your poles? So you started off with two poles that are real quantities at -1 over tau 1 and -1 over tau 2. I don't know which one is happening first. Depends on the values, of course, but let's assume that one happens before the other one, right? So that's where we started off. But look at what's happening. As you increase T0, their sum and product gets scaled, and you can see where they are with respect to each other, right? You can look at you can think about it different ways. You can look at the Q of this thing. You can see that the Q is actually increasing. Or you can think about it as a quadratic equation, just as a quadratic equation, and try to calculate b squared minus 4ac, right? What's under the square root, and see what's happening. And you'll see what's under the square root is actually decreasing with T0 as you're increasing T0. So as you're increasing T0, what happens is that these guys start moving towards each other, the two poles, as T0 is increasing. And at a certain value of T0, they actually meet exactly halfway in between. And that value, you can easily show, is T0 being tau 1 minus tau 2 squared over. So this is for T0 being equal to tau 1 minus tau 2 squared divided by 4 tau 1 tau 2. So at that value, I mean, it's a simple quadratic equation. You can evaluate it that way. So at that point, what you have is that they hit each other. And after that, Q, so this is where the Q, so this is Q of 1/2. Quality factor of 1/2. which is the borderline for poles becoming complex. So what happens after that? They split into a pair of complex conjugate poles, right? So they would go like that, and they will keep going as you increase T0. So the system becomes progressively more and more underdamped, right? Because now your zeta is decreasing, your damping factor. Your quality factor is increasing. So you can imagine that the response of the system, so this determines the response of the system, right? We are looking at the poles of this guy. The poles of the return ratio are fixed. They're at these two frequencies. These are the poles of the return ratio. But the poles of the overall transfer function go from an overdamped response, which is going to look slow, quiet response. They become critically damped, Q of 1/2, then become complex, then they become complex, and then basically you get ringing. So as you're increasing, so it means that if you make your T of 0, the return ratio, the DC low frequency return ratio, very large, your system starts acting very differently because of the feedback. And this is something that we'll talk about extensively when we talk about stability in feedback loop and stabilizing the feedback loop. But you can see that things are becoming a little bit more interesting now. You went from a response that was 2 time constant, something like this, you went to this, then you go to this, and then eventually you go to something that starts ringing more and more as you increase T naught, T of 0, your return ratio. So you can see it even but you can see all of that dynamics is something that you can evaluate by using time constants and understanding and being able to break it into smaller pieces. If you aggregate everything into this gigantic equation that has like a bunch of GMs and Rs and all those things, you won't see it. There's also, you have to remember, there's also a 0 in the transfer function. It's a fixed 0. It's a left half plane 0, so it's not horrible, but it would also appear in the transfer function. And you can play with that to induce certain effects if you're interested in doing things. You can actually get it to compensate some of the responses of the poles by placing in the right place actually. So because this is a parameter you can control, right? This is part of your feedback network. You can actually control what you do by controlling the relative values of R's and C's. So maybe you can use this 0 to compensate to some extent the behavior of the two poles that are induced when you have a large feedback network. That's one of the methods of feedback compensation in feedback loops. All right, any questions on that? Okay, let's do a couple more examples. I want to show you actually something else within another example. And then, yeah, let's do that. So this example is actually our first transistor level example that we did, which is I think, series shunt feedback network. So it kind of looked like this. R3, V in, and V out. This was, I think, R2 and R1. Let me just double check to make sure I haven't missed anything, what we wanted to have. Yeah, okay, so yeah, that's the one. And we are going to do the 3 calculations again for this, but we are going to do it 2 different ways. And we'll see the difference here. So one is the first time we calculated with the T model. We use the T model for this guy. So if you use the T model for it, the small signal model will start looking like this. I'm using a pi for that one because its source is grounded, AC grounded, V2 or V3, whatever. And then we have this one, and then you have this being IS1, and this is R3, this is V2. These are grounds. Okay, and this is Vn. So we choose this source first to be our source of interest. You choose one dependent source and you stick with that. Okay? So now if this k goes to infinity, for h infinity, this is the calculation we did before, right? So h infinity of this thing, if this, we've checked the sign of this feedback before, it's negative feedback. So to get finite output here, you have to have a finite voltage here. V2 has to be finite, which means that this current has to be finite. Now if k I1s is to be finite and k is infinity, is going to become very large, then is has to be 0. So it means that this current, I equals 0, and this voltage is 0. That was the asymptotic equality principle, right? It came from that, which basically tells you that you didn't do any of these things. If that k is infinity, this voltage has to be the same as this, which is basically V out division ratio. You have the division ratio. So this basically becomes 1 over R1 or R2 over R1, right? Because this division ratio here, if you remember, this has to be V out times R1 over R1 plus R2. But now that's because of the asymptotic equality is V in. And if you invert that, this is what you get, right? But if I want to kind of express it more explicitly, it's V out over V in when k is infinity, which is basically 1 plus R2 over R1. This we did before. This is the calculation we did before. Right? So that was the asymptotic function. Asymptotic transfer function, yeah. Now, what else do we have to calculate? We have to calculate the return ratio. For return ratio calculations, okay, we picked our source. We cannot change it. So we are going to basically say, now k is 1 for return ratio. So for return ratio, k is 1. Now, and then we are introducing this source. So this is Iz. So this is Ix, and this is Iy. So if this is Ix, this voltage is going to be negative Ix times R3, right? This current is going to be Gm times that. So this current is being pulled out of this node. So this current would be negative, or you can change the polarity. This current is going to be Ix Gm2 R3, right? That's Ix. Now, what fraction of that current goes through here? It's a resistive divider, right, between these two. So this current is going to be Ix Gm2 R3 times the resistive divider ratio, which is R1 over R1 plus Rm1. That's the current that's being pushed into this guy, which would appear exactly right there. So Iy is going to be negative of that. And now that we have our return ratio, right? So our return ratio is going to be negative of Iy over Ix, which is going to be Gm2 R3 R1 over R1 plus Rm1. Now, what does that mean? Well, again, it shows you that you have this ratio. You don't want it to become too small. And you have a Gm2 R3, Gm of this guy and R3, the product of the Gm of this and R3, which will determine how close you will come to the ideal calculations. You want it to be relatively large. Of course, when you are making it too large, then you have to be careful about the dynamics, which in this case we are ignoring because we don't have any capacitors. So that's the trade-off, which we'll come back to later. And then there's the H0 of this thing, right? H0. Is there an H0? So again, for H0, so let's just use a different color. For H0, we used orange, I guess. So H0. For H0, K is 0, right? So there are three calculations happening here. With K equals 0, if K is 0, basically this guy is gone. This is not there. And that one, of course, is not there. That's only for return ratio calculation. So that path is gone. The only way the signal can get from the input to the output is through here. But there is a way for the simple input signal to get from the input to the output, right? If you put a voltage V in here, you have a resistive divider here. And if this current source is 0, because this current was 0, so this is not going to do anything, these two voltages will be the same because there's no current flowing through this. So this voltage is going to be just a resistive divider here. So this is going to be R2 over R2 plus RM1. Is that clear? Just a resistive divider here to determine this voltage, because this current is 0, because this current source was 0, so this voltage became 0, so this current source became 0, so it became open circuit.
Shouldn't it be R1?
Yes, it should be R1. Thank you. Yeah, it's the resistive divider between R1 and, I don't know why I wrote R2. Thank you. Yes, it's the resistive divider is here. Okay, so we're done. You know the exact transfer function. You can try to combine them to make some sort of a bigger expression, or you can say, look, I know that I want this to be large and I want this to be small, for example. So that's how you design, right? And I want, for example, this to be 10. So I make this 9, I make this large, I make this small, and I will have something that's stable. I mean, first order. Or you say, look, you know what? I can't make this very large. The largest I can make this is like going to be 10. So I know that I'm going to have a 10 divided by 11 multiplied by this. So instead of making this 10, if I wanted it a 10 or whatever, instead of making this 9, I make this 10, so this is 11. So times 10 divided by 11, I get the 10. I compensate for that. I make a correction there. If you needed a gain of 10, and you know that you are not willing to make this greater than 10, so you say, well, okay, my return ratio is 10, so I am going to get a factor of 10 divided by 10 plus 1, which is 10 over 11, and I'm requiring a gain of whatever, a gain of 10. So now I know this is going to get multiplied by that, so instead of making this 10, I can make this 11. So when it gets multiplied by this guy, it becomes 10. Relatively straightforward. Right? Because, again, you've broken it into pieces.